This lecture covers the reading from that is due on Monday, chapter 23, sections 5 and 7. It also goes back and covers a little bit of sections 1 and 2. The first important point from this reading is that there's a specific mathematical relationship between the electric potential field and the electric field. That relationship is shown in this equation right here, that the change in potential between, the difference in potential between 2 points is related to the electric field, the value of the electric field at those points, and the separation vector, which starts at one point and ends at the second point. And there's an important minus sign in front. So you'll notice it's the inner product between those two vectors. That relationship turns out to imply that surfaces of constant electric potential, which are the dashed lines here, are going to be perpendicular to the field lines. We met those field lines in a previous lecture as one of the representations of the electric field. Let's start out by imagining that we have an electric field set up in space. So this is created by charges that exist somewhere far away, and these charges are fixed and they won't move because of anything that we might do in the area that we are investigating. And I want you to think about 2 points in space. Let's call them point A and point B. These 2 points are not occupied by a physical particle. They're just 2 empty points in space. There is a separation vector, which I'll call delta R. That's the vector which starts at the first point and ends at the second point. Okay, so now I want you to imagine then the electric field varies. It might vary in space, but its value at point A and at point B is roughly the same. Okay, so I'm going to indicate its value here at point A by drawing a vector which starts at point A. Now that electric field has roughly the same value at B and also at all points in between. So remember, the electric field has a value at all points everywhere. This is just its value here, and it has roughly the same value here and at all points in between. Now, in that case, there's a very specific mathematical relationship between the change in potential, or the difference in potential between the potential at point B and A. That difference turns out to be equal to the negative of the inner product of the electric field and the separation vector. Okay? So this is VB, which is the potential at this point, and VA is the potential at this point. In order for the potential to be relatively constant in this area, for that to be true, we require that this separation distance is small. By small, I mean it has to be small enough so that the electric field is relatively constant in that region. Okay. This formula can be used to solve a number of different problems. I'm going to point out a couple of features of it. To do that, or a couple of implications of it, to do that, I'm going to define the angle between these two vectors as theta, and I'm going to remind you that the inner product is of 2 vectors is equal to the magnitude of one times the magnitude of the other times the cosine of the angle between them. Okay, that's said and done. Let me consider a couple of different cases here. I'll leave that formula up here. Let's consider case 1, where the electric field is parallel and in the same direction as delta R. In that case, you can verify. I'll just draw a little picture here. We have E, we have delta R. The angle theta is clearly 0 in this case. And if you think about this formula, remember cosine of 0 equals 1. So this implies that delta VAB is negative. Okay? That negative is very important. That implies that the electric field points in direction of decreasing potential. In other words, if I had a a potentiometer or a voltmeter or something that could measure the potential at this point, if I move my point in the direction of the electric field, I would see that the potential decreases. Likewise, if I know that a potential decreases in a certain direction in space, I know that the electric field must point in that direction. Okay, the next case we're going to consider is when the electric field is perpendicular to that separation vector. In that case, we have delta R pointing up that way, we have an E going that way, and the angle there, theta, is pi halves. We know that the cosine of that is 0. Therefore, this implies that the potential difference as we move in that direction is equal to 0. Okay? That has important implications. So that implies that if we were to look at what's called an equipotential surface, and this is the set of all points in space that have the same value of the potential, okay? And I'll give you an example. Let's consider a region of space in which we have a uniform electric field. Now, if you can remember when we talked about field lines, those field lines will be parallel and evenly spaced in a uniform electric field. The equipotential surfaces will be planes perpendicular to that, and I'll represent those by a dotted line. So these dotted lines, they look like lines, right? But they're to be thought of as planes. So the field lines go in this direction, and they exist everywhere in space. They're equally separated, and you have some in front of the page and behind the screen also, in front of the screen and behind it, so that it fills three-dimensional space. These dashed lines are actually planes, which are everywhere perpendicular. And I can prove that the potential must be equal everywhere along here. If I were to pick one point, let's say here, and evaluate its potential, let's call that point A, and then I were to pick a second point, call it point B, you can see that the displacement vector between those is in fact perpendicular. So by the theorem or the result that we just derived, the potential difference at between B and A must be 0, so the potential at B must be the same as the potential A. And that exists anywhere on the surface. Even if I were to come out of the screen or into the screen, the potential on that plane should be everywhere equal. So this is one important case of that. In a uniform electric field, the equipotential surfaces are planes, flat planes, which are perpendicular to the electric field lines. Let me show you one more case, an example of equipotential surface. So that's one case, a uniform electric field. In this case, we're going to consider the electric field and electric potential of a point charge. So I'm going to put a dot here. That, in this case, is going to be a material particle with a positive charge, let's say. Let me draw some field lines through that. The field lines should be uniformly distributed and in straight lines, if you remember. So the electric field around a point charge points everywhere away, and it decreases in magnitude as we get farther away. So note the spacing between these lines gets larger the farther away we get from the point charge. Now then, you can ask yourself, what type of surface is everywhere perpendicular to these lines, which are everywhere diverging in straight lines from this center? So think about that for a second. The answer, of course, is that they are spheres. They're spherical surfaces. So I'm going to draw a circle here and here. These are just two surfaces. And you can verify, just by thinking about it, that as I move along this surface, the electric field is always perpendicular to that surface. So in a small region, when my delta R is small, so it's tangent to that surface, the electric field will be roughly in the same direction all along there because the delta R is very small, right? So the electric field is roughly constant. And it will be perpendicular to that delta R. Therefore, the delta V will be 0, and that will always be 0 for every little displacement I make along this sphere. And that will happen in any direction along the surface of the sphere, so the potential is constant. So in the second case, we see that the equipotential surfaces associated with a point charge are spheres, concentric spheres, which are centered on that point charge. I'm also going to point out that the potential here, let's think about how the potential changes as we move out. So let's look back at this uniform field. I've got a potential here, here, and here. I can label these with values. So let's say this surface, this first surface, might have a potential value of 1, the second one V2, V3, and V4. So what that means is that everywhere on this plane, the equipotential the electric potential has the same value as on this plane, and this plane, but they have 4 different values. Now I'm going to ask you, what's the relationship between these values? In which direction do the is the potential V1, is it different from V2? Is it greater than or less than V2? So think about that for a second, comparing V1 and V2. The answer, if you remember from what we discussed in our analysis of the implications of that fundamental relationship, when we consider delta R going in the direction of the electric field, so imagine now our delta R goes from here to here. Now the delta R is in the direction of the electric field, that inner product is positive, but there's a very important negative sign. So the delta V is negative. So in fact, in this case, we have V2 is less than V1, right? Because the delta V will be negative. And that continues on in this direction. So that relationship is true for V3 relative to V2, V4 is less than V3, etc. And if you can remember that rule, that in the direction of the electric field, the potential decreases. So the electric field points in the direction of the electric field, the electric field points in the direction of decreasing potential. The same argument holds here. Let's label these potentials V2 and V1. So the inner surface here has a potential V1 on it. This one has a potential V2. Again, if I were to make a delta R vector going from a point on the inner sphere to the outer sphere, that delta R is in the same direction as the electric field everywhere along here. Now the electric field does decrease in value. If these potential surfaces are close enough, then the magnitude of the electric field is relatively constant. Even if these potential surfaces are far apart, but the change in each little small displacement outward can easily be evaluated with that formula we gave. And each contribution to the change is negative because the delta R always points in the direction of the electric field. So in this case as well, you can see V2 is less than V1. And you can get to that result just by remembering that the electric field points in the direction of decreasing potential. Okay, let's test our understanding of some of these principles by taking a look at this problem. So what I'm going to do is I'll read the problem to you, and then I want you to take a couple of minutes to see if you can answer it. You can stop the video, take a few minutes, and then if you're not sure of your answer, you can start the video again. I'll give a hint. I'll give you a hint, and then you can stop and try again, and then at last you can start and I'll explain the proper reasoning. Okay? So go ahead and try to solve this problem. Now the hint that I'm going to give you is see if you can figure out in which direction the electric field points in this problem here, in this space here. Can you determine which direction the electric field points? Okay, now here's the proper reasoning here. Because the proton is positive, in an electric field, it will experience a force in the direction of the electric field. So if I could just figure out the direction of the electric field, I can figure out the direction of force and what direction it will start accelerating. So if we remember that the electric field points in the direction of decreasing potential, we can clearly see that the potential on this side is higher than this side. So the direction of decreasing potential is to the left, and that is the direction of the electric field. So it will experience a force, the particle will experience a force pointing to the left, and it will begin accelerating. You can also see that the spacing here is the same as here. So remember that the potential difference is not only proportional to the electric field, but also the distance between the two equipotential surfaces. So it will definitely start accelerating, and it will maintain that acceleration. So the correct answer here is it will move towards A with increasing speed. Let's try this problem here. Now, in this one, the dotted lines represent equipotential surfaces with a given potential value as shown below. Let me clarify this diagram here. This equipotential surface here has 50 volts, and then they decrease by 10 volts. So it's 40, 50, 30. This is 20, 10, and 0, but then it increases again, 10, 20, 30, 40, and then 50 volts. Okay? Which set of arrows best describes the relative magnitudes and directions of the electric fields at points A and B? Then you're given 5 choices, 1, 2, 3, 4, and 5, and 6, 7, and 8 down there. Okay? Okay, the hint here is to determine the electric field direction. Remember, it points in the direction of decreasing potential. And also, if you remember the formula that the change in potential is going to be proportional to the magnitude of the electric field times the displacement, okay? In other words, the magnitude of the change in potential is proportional to the magnitude of the electric field times the magnitude of the separation between the equipotential surfaces, okay? So think about the separation between the equipotential, and that corresponds to the delta R. Think about how E would have to change. Think about the delta V between these and compare that to the delta V here, and how E would have to change so you get the same delta V. Okay, so the correct reasoning, let me explain that. We're going to use the formula delta V, and I'm just going to think about the magnitude of the change is E times delta R here. And that gives me the magnitude. So this will help me determine which vector should be larger than the other. So if the electric field has a different value in one place than the other. If you look at these regions around here, this the potential difference between here and here and here and here, that's 10 volts. But it's the same here. As I mentioned, this goes 50, 40, 30, 20, 10, 0. It's 10 volts here also. So this is the same delta V in this region. If I were to make a displacement between here and here, say that's 20 volts. Then if I go across that position, that's also 20 volts. But the delta R is different in each case. In this case, delta R, the magnitude of the distance from this point to this point, I'm thinking about a displacement, say, from here to here, and compare that to a displacement from here to here. This is much larger than this, but the product of the two must be the same. So when the spacing of the equipotential surfaces is larger, and note these have to be equally spaced in potential, right? So this is a 10 volt difference here, there's a 10 volt difference here. When that potential difference is the same, the electric field is going to be inversely proportional to the spacing of the equipotential surfaces. And that just comes from this formula right here. That implies that this point B on the right must have a smaller electric field. Its magnitude must be smaller. So let's look at some of these conditions here. We can see that this one has the same. Anyone with the same obviously is out, and anyone that has it larger on the right is out. So that eliminates those three. Now then, let's think about the direction. If we just remember that the electric field points in the direction of decreasing potential, so the decreasing potential goes this way, let's point in the direction of decreasing potential. That way there. And here note that it's higher on this side and it decreases to 0. So in this direction, the decreasing potential is in that direction. So the directions have to be like this. And you can see that there is only one answer which corresponds to that. There's only one answer that has them in opposite directions, pointing sort of towards the center. So this is the correct answer.